Bit-level error detection and correction is one of the important services delivered in the link layer. But we have checksums in TCP and UDP in the transport layer and IPv4 in the network layer. What is the difference, and why do we need each? Bit-level error detection and correction is necessary because errors that might be caused by signal attenuation or noise may change the bit values within a frame. Link layer does not want to deliver a datagram to a network layer to proceed with its end-to-end delivery if it's already known to have problems. Therefore, the receiver side of the link tries to detect the errors. After detecting the errors, either the frame is dropped and sender is asked for a retransmit, or it is corrected if possible. Error correction up to a certain level is possible using extra bits that are provided for checking and correcting. How? Let's start with detecting first and proceed with how certain methods of detection can help detect the location of the flipped bit and therefore correcting it. To be able to detect errors, we need extra information that could enable us to perform certain validity checks. All the bits in a frame that might be flipped should be checked. This includes bits in the encapsulated datagram as well as the frame-making bits. For our discussions, let's assume the frame has D bits and we add EDC bits of redundancy for error detection and correction. At the sending side, EDC is calculated based on a link layer mechanism implemented in the protocol and added to the frame. At the receiving side, D is double-checked with the same mechanism with the EDC bits of the packet. Note that the bit errors might also happen on the EDC bits. The results of the recalculations and checking determines whether there is an error detected or not, and if we should deliver the datagram to the network layer or not. An important caveat is that not all error detection are fully reliable. There might be some errors that are undetected. This depends on the strength of our detection mechanism. However, generally, the more number of EDC bits might enable us for better detection. We are going to examine a few of such EDC mechanisms that can help us in error detection. One of the simplest ways of checking for errors is using a parity bit. Parity checking validates a certain number of bits with the value of 1 in the total number of bits. If we have D data bits and 1 parity bit, the entire D plus 1 bits are checked for a certain number of 1s. If the desired number of 1s in the mechanism we use within the D plus 1 bits is odd, we call the mechanism an odd parity mechanism. If the desired number of 1s in the mechanism within the D plus 1 bits is even, we call the mechanism an even parity mechanism. So, for example, in the figure, if we are using an even parity mechanism, we expect even number of 1s in the D plus 1 bits. So we do have 9 1s here. Therefore, the parity bit at the sender will be set to 1. If when received at the receiver, we count an odd number of 1s, we will detect an error. If the counting at the receiver shows even number of bits, we conclude no errors. This mechanism can detect a 1-bit flip or odd number of bit flips, as we discussed in the example. That is not true for even number of bit flips. So, not detecting an error does not mean it has not happened. This is especially true for burst errors. Therefore, parity checking is a very weak detection mechanism that might miss the bits flipped. We can apply the parity mechanism in a two-dimensional setting, means applying a parity bit for each row and another parity bit for each column. If all of the rows and the columns remain the same, all row and column parities will validate the same. But if a single bit flip happens, it will affect two parity bits, the parity bit of the row and the parity bit of the column. This will add the possibility of finding the location where a bit flip has happened. If we can locate the bit flip, with the help of mechanisms like FEC or forward error correction, we can correct the flipped bit. However, two-dimensional parity is still not a very strong detection mechanism. Can you think why?